Now this session it'll be the last theorem in this section, so section 4.1, and the next section will be the famous halting problem, Turing's halting problem. So it's much the same vein as we've been doing all the way through. So it's been a pretty consistent pattern so far. So we're just showing that a particular language is decidable. In other words, the usual thing: find, construct, proof by construction, find or construct an algorithm, a Turing machine in other words, that accepts every element of the language, every member of the language, and rejects any other string. Language is a set of strings, so all the elements of that language are strings. So the Turing machine would reject any other string that's not a member of that language. Okay, so in this case the language is a context-free language. And what does that mean? A bit of revision. A context-free language, go back to chapter 2, what is it? It's the set of strings that can be generated by context-free grammar. Context-free grammar, remember, the rewrite, the overwrite rules, the substitution rules, in a context-free grammar, the left-hand side of the substitution rules have only one variable. If you have more than one, it's no longer context-free, it's context-dependent. Okay, so how to show that context-free grammar is decidable? How to prove that? Decidable, a language is decidable. Again, a bit of revision, I've done this many times, but just to ram it home so you really get the message. So how could you make a context-free language, a C of L, decidable? What would that mean? It means you find a Turing machine that would accept every string of that language and would reject any other string that does not belong to that language. And effectively that would then answer the question, does a particular grammar, a context-free grammar, generate a string? So is the CFL decidable? I'm thinking a bit real time here. Maybe I should, my brain's starting to fuzz. Maybe I need some water, just a minute. I should refuel my brain somewhat. So how to decide whether a context-free language, how do you prove that it is decidable? You create a Turing machine that will accept every string in that language and reject every other. And how to do that? So your Turing machine would have to take a grammar, take a description of the grammar, and then use that description, create a Turing machine that behaved like a grammar, with substitution rules and so forth, and a set of terminals and a set of variables, all the things about a grammar, context-free grammar, and then use that on to show that any string that belongs to the language can be generated by the grammar. I guess that's what it boils down to, because that's what this means. Okay, so you can find thinking real time here. You can find a Turing machine that recognizes the language. Now, wait a minute, we want more than recognizes. We want it to decide. It's got to be more than just saying, yes, this particular string does belong to the language. But it has to do more than that. It's got to be a decider. Right? It's not just a recognizer. What I've just said is that's a recognizer. You also want the machine, the Turing machine, to say this particular string is not a member of the language. In other words, this particular string cannot be generated by the grammar that corresponds to this language. Yeah. A C of L is the language of a particular CFG, a particular grammar, context-free grammar. The grammar generates the language. It generates, by derivation, it generates all the strings that belong to that language, belong to that set of strings. That's what a language is. Okay. All right. So how to generate this this Turing machine that shows that for each string in the language, that string can be generated by the grammar. How to do that? Okay, we're sort of focusing, tuning in, focusing in on the problem. How to go about doing that? Well, a grammar. Let's see. Now, for a grammar, there's you can simulate a grammar with a PDA, with a stack-based machine. Right? We did that in earlier lectures. So in other words, a grammar and a PDA are equivalent, and we proved that at length. You can generate a PDA, a stack-based machine that behaves like a grammar, right? And okay, so that's sort of a core idea, maybe. We're sort of exploring here. Okay, so one suggestion is take your grammar, your CFG, and convert it into a PDA that behaves like the grammar. So the two are equivalent. So you go from a grammar, the CFG, to its equivalent PDA, a stack-based machine that behaves like the grammar you're talking about. Okay. Now that's still not a Turing machine. Now we've got to find an algorithm, right, that decides this language. In other words, a Turing machine that looks at each string of the language and says this string can be generated by the grammar. That's what it boils down to. So you have to find a Turing machine. Now so far we've only got as far as a PDA. That's not a Turing machine. PDAs are not Turing machines. Turing machines have infinite access to infinite memory. They have a tape. Whereas a PDA, push-down automaton, that has a stack. And stacks do not have infinite access to memory. They only have access to the top of the stack, much more limited. Right? So PDAs are much less powerful machines than Turing machines because of that limitation of access to memory. All right. So we could go a step further and have a second conversion. We could convert from the PDA to a Turing machine. And that's pretty easy. I mean, you can simulate with a tape the behavior of a stack. I think we did that, didn't we? I think we had a Turing machine behave like a PDA. Yeah, Yeah, I think that was I've done so much stuff I'm beginning to forget. Okay, so one idea is like a two-step conversion process. Convert firstly the grammar into a PDA, and the second step is convert the PDA into a Turing machine, and then have the they're in this two-step process. Then you've got the Turing machine behaving like a grammar via the Turing machine is simulating the PDA, which is simulating the grammar. Therefore, it's transitive. Therefore, the Turing machine is simulating the grammar. Right? You just cut out the intermediate step. So, and what do grammars do? What do they do? What are grammars? Well, they're generators of strings. Okay. So, in other words, you'll have this Turing machine generate strings, and so it can generate if it can take the grammar G, and if using that G, if it can generate a string W for all strings in the language, and reject, not generate all other strings, well then your Turing machine is a decider. It makes a decision, yes or no, whether a particular element that's in the language can be generated by the grammar. That's what you're trying to find. All right, that's the suggestion. But hold on, there are a few more comments. Okay, so convert. So convert your grammar into a PDA, and then your PDA into a Turing machine. Okay. Now that's not too hard to do, because simulating a stack is pretty easy, because a Turing machine